Well, here we are at class number 9, talking about firing of ceramics. And we're up into the kill and combustion section of the course. If you like hardware, you're going to begin to like the course a lot better because we've spent a lot of time talking about chemical reactions and transformations of processes and centering. Right now, we're talking about putting heat into a kiln, fire into the box, if you will, and then we're going to try to control that amount of combustion that's taking place and deliver to the ceramic the temperature and the heat work that's required to make a quality ceramic. So today we're going to talk about fuel combustion, a little bit of chemistry here and combustion, and then we're going to go to burners. Where we're trying to concentrate the fuel. So bear with me and we'll go forward. I wanted to start this particular class with a quote from the North American Combustion Handbook in the introduction. And it really refers to, in all the time before the modern era, there were people that burned fuels that were convenient, particularly solid wood, maybe coal, through an opening in a furnace called a burner, and they burned it at the rate that it would burn naturally. After electricity came into societies, and after natural gas became abundantly available, which is typically after World War II era, then we were able to design special burners which concentrated the heat into a certain area, and combustion was very, very fast. It was so fast that we could then begin to make product at a much higher rate than was possible in all the societies before. So that's basically where we are today. We're trying to figure out how to produce that heat and concentrate it in one place. So we're going to talk about some combustion fundamentals first in the first part of this particular class. And of course, to release heat, we use oxidation of a fuel in order to release that heat. We're going to mainly talk about gaseous fuels in this course. But we'll mention solid fuels and liquid fuels as well. But nevertheless, the rule of thumb is that you're going to see today about 10 parts of air required to completely combust 1 part of natural gas. That's a rule of thumb. It's something you can easily remember, 10 to 1. And that will release about 1,000 BTUs, a little over 1,000 BTUs per cubic foot, CF in the slide, of natural gas. 10 to 1, 10 parts air to 1 part gas, and 1,000 BTUs per cubic foot of gas. Easy to remember. Well, you knew it was coming. We have to talk about chemical reactions. And here we're going to talk about the oxidation or combustion of methane, CH4, methane as a gas. Methane is the main component of natural gas that releases heat. It's present in other gases in our environment. But nevertheless, let's talk about using oxygen, O2, the diatomic molecule O2, oxygen, pure oxygen, to burn methane. And so you can see the chemical reaction which is in the slide. CH4 plus 2 O2, that's 1 mole of methane to 2 moles of oxygen, produces 1 mole of carbon dioxide and 2 moles of water plus heat. Now, mole, that's a gram molecular weight. It's a defined quantity of substance by weight, but we're really interested in volume, and a mole of gas has a certain molar volume no matter what the gas is. So therefore, the mole ratio of oxygen to methane in the combustion equation is the same as the volume ratio of oxygen to methane. And in combustion in air, that ratio of oxygen to methane by volume has to be 2.0 to achieve complete combustion or theoretical combustion. Now that has a special terminology for us, and we'll call it stoichiometric combustion. Stoichiometric combustion means that we have followed this equation exactly. We've reacted 1 mole of methane, 2 moles of oxygen to get the reaction products here. That's own stoichiometry. The ratios are correct for complete combustion. And actually, that's called own ratio combustion. Now, we'll talk about ratios as we go along today, but you need 2 parts of oxygen for each part of methane for own ratio combustion. And if you deliver more oxygen than that, it says air, but more oxygen than that, in this example, we're providing excess oxygen or excess air. And typically we might abbreviate that in English as XCA, excess air. Okay, well that's pretty easy. The rules change a little bit when we start combusting methane, a fuel and oxygen, because there's nitrogen in the air. So we're going to see that CO2 and H2O are the products of combustion, but now nitrogen is there too. It may have participated in combustion to some degree, forming nitrogen oxide species, but at lower temperatures, it's just going to pass through as nitrogen and will liberate some heat. So think about the ratio of nitrogen to oxygen in air. We've talked about air previously in the drying course and in this course, and the ratio of nitrogen to oxygen in air by volume is 3.71 to 3.76. In other words, there are 3.71 to 3.76 parts of nitrogen by volume to each volume of oxygen. Most people just use 3.76 in their calculations. And so that's what we're going to use today, particularly as we go into the next slide. Well, here's an example of the stoichiometric, wow, that's quite a word, stoichiometric combustion of methane. That means own ratio combustion. So that means CH4 plus 2, but now we don't use oxygen, we use 1 of oxygen plus 3.76 parts by volume of nitrogen. So this now, where we had oxygen before in the previous slide, we now have air. So look what we have here for each part of methane. We have 2 times 1 of oxygen and 3.76 of nitrogen. So 1 volume oxygen, 3.76 volumes of nitrogen. That's a total of 4.76 volumes times 2. And if we do that arithmetic, we end up with 9.76 parts of air to 1 part of methane. Okay, let's say it again. 3.76 plus 1 is 4.76, but we needed twice that much. So that turns out to be 9.76. I hope I did that arithmetic correctly, but it's not important because what we're going to end up with a rule of thumb that we use about 10 parts of air to 1 part of methane. Okay, so in most gas-fired heaters and natural gas-fired burners, a ratio will be computed for stoichiometric combustion of 9.4 to 11 cubic feet of air per 1 cubic foot of fuel. It depends on the chemistry, chemical analysis of the local natural gas that you're using. And we'll just abbreviate that as 10 to 1. 10 parts of air for 1 part of oxygen. And if we combust like that, we'll find a little bit of excess air in the flue gases, meaning the smokestack, about 2% oxygen. So we know at that level we have complete combustion. Okay, so typically we use oxygen analysis on the flue gases from time to time to make sure that we're combusting all the fuel. The fuel costs us money, so therefore we want to make sure we get all the heat out of it. We don't want any unburned fuel coming out of the kill. That would contribute to greenhouse gases and be considered pollution. So we typically want a little bit of oxygen in the flue gases that are exiting the kill. And typically we'll use a little bit more oxygen, maybe 5 to 10% excess air in combustion in a typical combustion situation. That'll give us a little over 1% oxygen in the flue gas. Well, that's pretty simple. Okay, 2 times 4.76 is not exactly 9.76. I apologize for the arithmetic error, but nevertheless, that's the deal. Okay. Suppose we use 25% excess air. So in that case, we take methane and 1.25, 125% or 1.25 parts here of air, 3.76 nitrogen to 1 part oxygen. And this is what we get in the flue gases, carbon dioxide. If we've completely oxidized the material, water vapor, a little bit of oxygen left over because we had excess air, and a little bit more nitrogen. And so the actual gas ratio of air to fuel is about 12 to 1 with 25% excess air. Okay. Why do you need excess air? Well, I've mentioned complete combustion. That's certainly a reason that we all would logically think of. But the other reason is combustion takes place really rapidly. And although we try to mix air and fuel in the burners, as you'll see in a little bit, sometimes some of the air that's present in that mixture escapes without participating in combustion. So we have to add a little extra air in order to do that. And so that's really the reason we use excess air, is we need a little excess air to be sure that we've provided enough air for each unit volume of fuel to get complete combustion. Now here's a table I found on the internet, combustion ranges for common gases, and you can see methane, the stoichiometric ratio, own ratio is 9.53 parts by volume of air per part of fuel. Natural gas has a little range, 9.4 to 11, depending on the chemistry of the natural gas. Interestingly enough, propane takes a fair amount. The chemical formula for propane is C3H8, and so it has more carbon to burn in that process, requiring a little more air. Coke oven gas, which is mostly carbon monoxide, by contrast, requires lower amounts of air per unit volume of gas. The heats of combustion are up here, around 1,000, once again, for methane and natural gas, depending on the gas source. Propane is higher, 2590 BTUs per cubic foot, whereas coke oven gas is a lot lower. So the ratios that you use depend upon the fuel that you use, and this is important because in a lot of cases propane is used as a backup fuel for natural gas. Now, in the same line of thought, here's some combustion ranges for oil and coal. This was stated as air cubic feet per pound of fuel. That's a little different for us to comprehend, but we get some heats of combustion here that are BTUs per pound, and you can see that these liquid and solid fuels are packed with the potential to supply heat. I added this little table over here in the slide. Typically with fuel oils, we'll use excess air, perhaps in the 40% range or thereabouts with fuel oil. Whereas remember with natural gas, we're around 10% excess air. Now we're up higher percent excess air with fuel oil. And the main reason is we're trying to burn all the oil and prevent soot. Soot being a submicron particle, it will color exhaust gases. It's unhealthy, perhaps for human health, and so we typically use more excess air to get complete combustion of the fuel oil. With solid fuels, things like coal and perhaps wood dust, wood flour. We use a lot of that in making bricks in the United States. We can use 100% excess air, particularly in a tunnel fuel. So the amount of excess air in part is determined by complete combustion of fuel and pollution reasons. Okay, well, remember last time we talked about calculation of adiabatic fuel temperatures, and this time we're going to use e-solutions. We can do this manually, but this is the modern world, so why not look at combustion with a few fuels using the e-solutions, Honeywell e-solutions combustion utility. Now, here's an example that I used East Ohio Natural Gas. Okay, so I've selected that fuel here in the fuel data utility. This is example number 1, a gaseous fuel, and we've got the computer data for the combustion of natural gas East Ohio, which I used to buy when I lived in the upper Midwest in the United States. Notice that we have gross heating values of 1,031 BTUs per standard cubic foot. If you want to see the definition of standard cubic foot, you can go into the nomenclature app, okay? So the gross heating value is 1,031, but the net heating value down here is only 935. Remember, the gross heating value considers all the heat that is released, but the net heating value includes the fact that you have to heat up the water vapor that's present in the fuel and the products of combustion, carbon dioxide. Each one of those substances has a specific heat, so it must be heated up to the combustion temperature. And so that's the net heating value is the amount of energy that you can use in combusting this fuel. So in this fuel combustion utility, we went away from the fuel data. In the fuel combustion utility, we've gone to it and selected a standard gas, East Ohio gas. I've selected 10% excess air here for my combustion situation. The air temperature is 60 degrees Fahrenheit, which is kind of a normal plant temperature mid-season. And I've selected an exhaust temperature of 2,000 degrees Fahrenheit. That might be high, but if you were exhausting, say, a batch kill into a laboratory, that might be reasonable in firing ceramics. I chose the fuel temperature as the exact same temperature as the combustion air temperature, in other words, room temperature. The other thing that I did was I selected 1 standard cubic foot per hour, okay, the fuel input. Now, I like to do that because I like to look at results in terms of per standard cubic foot of fuel. But if you wanted to use an actual fuel consumption that you're using in your device, your kill, you can enter any number here that you want to. Further, I didn't choose to enter any ambient conditions. If you're using combustion air with a higher relative humidity, you're going to get less net heating value out of the fuel because you have extra water vapor to heat up. Well, of course, the eSolutions is going to give you a paper report that you can print for your records. And this is half of it here. We talked about, we provided the fuel composition that we chose for East Ohio natural gas. That gave us the gas gravity. Remember, that's the specific gravity relative to the specific gravity of air. So the gravity of this gas is lower than that of air. That means if it's released, it's going to go up by buoyant effects. We have the gross heating value and the net heating value given in this situation. The theoretical air required is 9.87 parts of air per part of East Ohio natural gas. We're actually going to choose excess air in our calculation. And so here's the information provided to us, 10% excess air, and it records all the data that we were using in this particular situation. Okay, so having said that, we also can pick a liquid fuel. Now, there's a lot we can do with liquid fuels. I suppose the amount of liquid fuel used in the world has declined somewhat in more recent years. But it is used in certain areas of the world where petroleum is produced. Perhaps there is some other situation where waste liquids are used, like cooking oils, for example, or vegetable oils. So I chose a liquid fuel, and I chose number 2 fuel oil, which is very similar to diesel fuel. I chose excess air of 40%, a combustion air temperature of room temperature, fuel temperature the same, and a combustion temperature of 60, and I did it per gallon. So when I did that, the fuel data is that I have a gross heating value and a net heating value. We can see the fuel composition. Composition immediately tells us with sulfur components, we're going to have some sulfur emissions in our kiln. We could have soot emissions as well, since we're using a liquid fuel. And of course, our data here is reserved for us for our record purposes. Now, having talked about combustion, the second part of this particular class is about burners. We got to deliver and direct the heat through a burner into a kiln. So remember, a burner is going to be a physical component that injects the combusting gases into the kiln or furnace that we're using. So there are several components. Since we're in ceramic kilns or furnaces, usually we're going to have a ceramic burner tile or refractory component to contain the gases and the flame. There's going to be a metal housing that allows us to connect that burner to the kiln or furnace shell, the outside of the kiln. We're going to have connections for gas and air supplies. We're going to have an ignition device, and we're going to have flame safety devices. Typically, we'll have other things like an observation port. So I'm not covering them all in this little summary. But they're designed to function by delivering a certain amount of heat, in our case, BTUs per hour, in a defined location in the kiln opening, kiln shell, the kiln design. Now, I'm not trying to make a kiln designer out of you in this situation. I'm trying to help you understand. Being a kiln designer requires a lot of experience, and I respect those folks a great deal. So as we talk about combustion systems in this course, we're going to determine the heat required, and we're going to put off number one till a little bit later in the course, because there we've got to provide the heat for the ceramic process, which we can calculate or measure. We're going to have to define the energy storage and the energy loss from the furnace. So we're going to put off number one. Number two is select the burners to supply the heat and place them in the furnace. We're going to talk about burners today. Later on, we're going to talk about supplying the fuel, meaning the lines, which is what I refer to as the plumbing, valves, regulators, and safety systems. So that will be next week. Supplying the air next week. We're going to get into controlling the fuel sources after that. We probably won't talk much about kiln pressure, but nevertheless, we know that when we inject these gases into the kiln and the heat is released, we're going to expand the gases quite a bit, and that develops the pressure within the kiln. In a lot of cases, we want to control that pressure in the kiln, maybe have a little bit higher pressure in the kiln to encourage heat transfer. So maybe we don't. We're going to talk later in the course about testing the flow in the combustion system. We're not going to talk too much about the kiln control. That should be in manuals and training aids supplied to you by the manufacturer of the kiln, and they should certainly address safety devices. We're going to talk about verifying the thermal profile of the kiln, maybe using thermocouples and parametric products, cones, in other words, or fire check keys. And of course, we're not going to talk about safety manuals and personnel training. That is part of your company's responsibility. So that's where we're going. We're just doing burners today, and the plumbing part next class. So this is pretty elementary. You know that the purpose of a burner is to provide placement of the flame at a certain location. Those locations are picked based on making sure that we have good heat distribution in the kiln. We don't want all the hot air to be at the top of the kiln. We're going to create turbulence within the kiln environment to try to make the gases move around. We may put the burners in the crown of the kiln, the top of the kiln, the side. We may fire underneath. We talked about that. A burner proportions the fuels. A burner mixes the fuels and provides a source of ignition. Burner provides flame stability and provides a means for control of the combustion situation. Each burner that's manufactured by a company like Honeywell Hauck is going to have certain operating parameters, and there's going to be a bulletin for each burner type, each particular model, that explains the minimum pressure, the maximum pressure, the airflow rates to maintain a stable flame. If you don't, then you'll have a flame out situation. So the purpose of the plumbing section is to provide air at the flow rates that are required to make the burner do its job. Now, I want to certainly give North American Thieves, North American, all due credit, because I've used a lot of images from their Combustion Handbooks volumes 1 and 2. I'm doing this only for educational purposes. This is copyrighted material. My understanding is I can provide that to you for educational purposes while giving full credit to Thieves North American. Any copying you do of this material is according to your own copyright policies of your organization. I urge you caution to not violate any copyrights. One way to violate it quickly is to sell the material and profit from it, and then you would certainly be in violation. So let's talk about various burner types. We're going to talk about air heaters to start with, and the first burner type might be a plate type. Okay, so here's a steel shell. The combustion environment is around to the right, and we're simply inserting gas, or some people might call it raw gas, through an opening into a combustion environment. So we assume that we're above the auto ignition temperature of the gas, and so it's going to burn. Somewhere we have to add air into this combustion environment so that we can maintain combustion. Remember, all the air for combustion has to be from the inside of the device. There are also pipe type burners. When I entered the refractory industry, these were used in tunnel kilns and some of the older kilns where an opening in the side of the kiln was a burner opening, and a gas pipe, raw gas, was injected right into the kiln, and it combusted due to the content of air within the tunnel kiln. So raw gas injection is one way to heat a kiln. You just got to make sure you have enough air present to complete the combustion. Another burner type is a ribbon burner. A ribbon burner shown in section is right here. So here's the burner pipe. In this case, they've said a premix of air and gas will be flowing out of the burner, and the flame is over in this direction right here. It really makes more sense to me to show you a picture of a ribbon burner. This is one here that I captured from the internet. So there's a gas pipe with openings in it and lots of flame being produced here. So ribbon burners might be used in a drier device, not in a kiln perhaps, but for low temperature heating of materials. These raw gas burners or ribbon burners might be used in those devices. I like to compare this to the burner in my gas grill that I produce barbecue in. I'm not the best cook in the world, but nevertheless, there's a ribbon burner in most gas grills that are used at home. And actually in most gas ovens. Now, here's another burner type, and this is a radiant tube burner. So there's a oven or furnace environment here, and all the flame and combustion is in an impervious tube. So it's like a baffle, but the heat transfer is from the surface of the tube out into the furnace environment. So sometimes in manufacturing of products containing carbon, you might use a radiant burner with a silicon carbide tube here because the temperature is involved. But nevertheless, The diagram shows a premix of gas and air being injected into the tube with air being brought in as well into the tube enclosure for combustion to take place. Still haven't gotten to the types used in most kilns yet. Now here is a nozzle mix burner, very common in perhaps older applications, but they're still used today. And so we're seeing this burner in section. So the kill's out here and the burner is attached going through the refractory lining of the kiln and attached to the outside of the furnace. The refractory tile is shown here because combustion is taking place in part in the tile. We have combustion that goes out into the kiln. And so in this particular case, we're injecting air, shown by the blue arrows, around the periphery of the burner tile, and gas being injected into the middle. Why do we put air around the periphery? Well, it provides some cooling effect for the refractory, and therefore we've enclosed a flame in a shroud of air, so to speak, as it's coming out of the burner. So these burners were very prevalent in the ceramic industry when I came into it. And of course, burner types have really changed a lot over the years. Here's a premix burner. Here, the burner is protruding through the kiln and attached to the outside of the kiln, but premix means a mixture of gas and air coming into this premix chamber with combustion taking place in the burner tile. So this is a normal burner. We're not showing the means of premixing out here because those can vary a bit depending on the type of burner. And we have a large opening here for this burner. And modern technology, we've placed a refractory constriction over this, so a small opening, so that combustion takes place here, but we push the products of combustion at very high velocity out into the load. So that's called a high velocity burner. That's a variation and a much more modern adaptation of this burner type. And finally, last but not least, showing a flat flame burner. Flat flame burner is just exactly what it says. Gas and air are injected into a refractory area, but there is a diffuser plate in this burner. You can see it up here trying to concentrate the flame right in the middle of the burner and let it flow outward, okay, and produce a flat flame. And here's a picture of one that I found from the internet. Not exactly sure what all this high temperature stuff is out here, but the blue flame is typical of the gas flame in this particular situation. So, I mean, do you suppose that that's light coming from the outside of a furnace? Wow, a very good control of that situation. Now, some good pictures taken from North American Combustion Handbook are pictures of gas flames coming out of a burner, and they're comparing different fuel consumption rates up here at 10 million BTUs per hour, fuel for heat production, down to, well, that's supposed to read 1 million BTUs per hour. And so you can see how the size of the fuel changes, how the size of the flame changes as you change the heat output of the burner. You burn a lot more fuel, use a lot more air, and so we have a bigger flame. Sometimes these flames are called stingers because if you get in their way, they're going to sting you. Not just the flame itself, but the products of combustion can sting you coming out or burn you coming out of the flame. Now the flame profile is a little bit different at 60 degrees Fahrenheit. Okay, faster combustion at 800 here in the environment, a little bit slower combustion out here at 60 degrees Fahrenheit. But those are natural gas flames. And full credit to North American. This is from volume 2 of the North American Combustion Handbook. Now, of course, these flames are blue, okay, typically around the outer edge where combustion initially takes place very rapidly, and a little bit lighter toward the inside core of the flame. But here's some oil flames. And again, we have the same heat outputs. I didn't note these on the slide. Low output 1 million BTUs per hour, 10 million BTUs per hour. This is the high temperature situation, 800, and this is the low temperature furnace situation. So you can see the flame profile changes depending on the temperature and the fuel output. But there are another couple of things to notice here. Notice how jagged the flame is here. Looks like a feather almost. And that means that combustion is taking place not in a uniform manner right on the front of the flame, particularly at low temperature. Another thing to notice is the color of the flame. Very typical of oil flames to be yellow in color. What's happening here is that we are having unburned hydrocarbons, polymeric fuel fragments toward the center of the flame, and they are absorbing some of the energy that's being emitted during the combustion process. So this gives us a yellow light appearance in combustion. Now, the Hauck people were very kind to supply me with a cutaway burner, so to use in my classes at the university. So they've cut away the burner tile here. You can see the refractory part that's forming the combustion area in this nozzle mix burner. It's a nozzle mix burner because you can see the air inputs. There are 2 of them here, and the air in the primary input comes here and shrouds the flame around here. So it's 360 degrees shrouding the flame as it comes out into the burner. Now, when we're combusting natural gas, the combustion of natural gas input is here, and it comes around this mechanism, and you can see the yellow painted area here to illustrate that's where the gas and the air would mix at the nozzle. Now, this happens to be a dual fuel burner, so therefore an orange color is the color used on piping for oil. And there's a little shroud here in the oil chamber because oil has to be vaporized, changed from a liquid to a vapor as it passes into the burner. It uses the heat from this housing to vaporize, and then some air is injected into that oil chamber in order to push that vaporized oil into the burner. So you can operate either with air combustion and fuel, natural gas, or air combustion and oil in this burner. You can see it a little better in this cutaway. Particularly, you can see how the air surrounds this burner housing at air plenum, surrounds this burner housing, and air is injected through these openings into the burner. But now you can more clearly see where the gas comes in if we're operating only on gas through the gas line into the burner. But if we switch over to oil and the gas supply is shut off, then we have the oil coming in here as indicated by the orange. There are perforations in this pipe. The shroud around it contains the oil vapors. You can see some of the perforations in the pipe here. It's been cut away just for demonstration purposes. This injected into the fuel area of the burner. And of course, the air to sweep the oil vapor is coming through here. Dual fuel burner, the oil would be a backup fuel in this particular situation. Now, each burner has a burner bulletin. This was the MC200 series burner. Back when Hauck was an independent company. I'm sure that Honeywell Hauck is illustrated on the burner bulletin today. And this bulletin gives a lot of information, particularly the air volume requirements, gas volume requirements, pressures that are required to maintain a stable flame, the burner output, as you can ramp up the output using more and more air as the air and gas are changed in volume as they're injected into the burner to get more heat. We'll talk about that in burner control section of a later lecture. This information also has information like flame lengths. It will give replacement parts and information, maybe safety information. So that's what you get. Now you can recognize burners by taking a look at them when you're walking through a kill. This is a demonstration device that I used in teaching. It was originally provided to my university by North American Manufacturing. So you can see a centrifugal blower, which is going up into a blue colored pipe with air going down to the various burners. So one of these would be burned at a time. We're going to talk about the plumbing next time, so you'll see the backside of this burner. So this is a refractory wall. The burners are located through the refractory. And so the first burner to be noted here is a nozzle mix burner, standard one like we just talked about with a Hauck burner. You can see the size opening here that is shooting a flame directly towards you whenever you're operating that burner. The students always like to see the demonstration. A flat flame burner, you can see the curved face of the burner, so that's a dead giveaway that we have a flat flame burner used in a combustion device. An excess air burner is used where we're trying to use a lot of excess air to make sure that the temperature of the flame coming out is lower than might be produced in a nozzle mix burner. Then finally, you can see the high velocity burner, which is basically a nozzle mix burner with a refractory plate and a small opening, and that is designed to shoot a stinger out a long distance. And they're very useful in having uniform temperature control in a kill. Now later on, we're going to talk about intermittent firing of burners. Sometimes these are called step fire burners. I think that's one of the trade names, where the burner shuts on and off intermittently as a means of getting the best possible fuel efficiency and the best heat distribution in a furnace. And like I say, we're going to talk about the backside of this burner and trace the lines. Trace the lines meaning goes backward from the burner through the control valves, through the adjusting valves that we have available to us, through the shutoff valves, to the fuel source, and back to where fuel comes into the plant or the area of the plant that you're operating in. We're going to trace the air back through its various control dampers and actually to the blower. And so that's what we're going to do next time, trace the lines, and we're going backward. Remember, the logic of the course was you start with the heat required inside the kill, then we talk about the burners and their placement to supply the heat, then we talk about the plumbing required to get the gas and air or other fuels to the burner back to where the fuel comes in the plant. Okay, well, reviewing just a little bit for today. Today we talked about mainly the air to fuel ratio required for complete combustion. And you've seen that we use a little bit of excess air to get complete combustion, and the ratio will depend on the type of fuel that we're using. Sometimes with liquid fuels, we'll use much higher excess air in order to get minimize soot production, to get good environmental compliance. And with solid fuel combustion, we may use even much higher excess air in the kiln. We talked about the types of burners, and we identified some of the key components like the burner tile and the burner housing, and some of the connections. We did look at one nozzle mix burner shown in the cutaway. So the next time we're going to talk about the combustion system components. I've called that the plumbing, and we'll talk about flame supervision, in other words, safety equipment. So I really suggest you read part 6 in the newer North American Combustion Handbook, Volume 2, and this part 6 is called Fuel Burning Equipment. I give North American Combustion a lot of credit for providing these pictures that we've looked at today. I recommend that you obtain the North American Combustion Handbook, which you can do on Amazon, a used bookstore, in your company library, or perhaps through the Thieves North American Combustion website. Okay, next time we're going to talk about plumbing.